everyone, I'm Dr. Likha Chandran, working as an assistant professor in the Department of Chemistry at VNR VJEC. In my previous class, we talked on polymers, the definition of polymers, monomers, polymerization reaction, and classification, and one mode of reaction or mode of polymerization, addition polymerization with an free radical mechanism. So in today's class, we'll be dealing about more details or like what is meant by the biodegradable polymers. Yes? So let us start our presentation. Yes, you although like we have seen polymers have revolutionized human life, right? They have created serious environmental challenges. Even though they have revolutionized, they have created serious environmental challenge. Many conventional plastic, what happens, degrade very slowly. So unlike organic waste, which decompose quickly, many polymers may persist in the environment for hundreds or thousands of years. So what happens as they slowly break down? They form microplastic that contaminate water, soil, and food chain. This has become a global concern. So what people did? So they are like our scientists, they are actively searching for sustainable alternatives. So this alternatives are like, that is what it is showing in the picture also. You can see that in a seashore, we can see like different types of plastic materials, bottles, right? So each part of that plastic bottle will be of different polymers. So what happens? This pollution is very high. So polymer degradation, which is like a simple example, like it is a process by which a polymer loses its chemical structure, molecular weight, mechanical strength, appearance, or functionality due to the environmental factors. This is known as polymer degradation. But let us see how long it has to be. See the numbers in the table. Polyethylene, which is a normal plastic bottle, right? It remains in the environment for several hundred years. Yes, slowest degrading. Think of PVC, which is which has to be remain or like which remains in the environment for 1,000+ years. Highly durable because like it is having chlorine content very badly. So slowly only it will degrade. Teflon, which we use in our cookwares, like non-stick cookwares, it can be degraded or like it will stay back more than 2,500 years up to. So highly stable polymer, chemically highly stable, yes, because of the fluorine bonding. So it is like all these polymers, polystyrene, polypropylene, PET, like polyethylene terephthalate, or nylon, all these are like taking years and years. Yes. So what will happen? Imagine throwing a plastic bottle today and it still exists when many future generations have passed. What will happen? This plastic pollution or like this plastic will cause a pollution to our environment, right? Which is again a global challenge. So now, what is the solution for this? Is there any solution? Yes? Is there? So the solution for this is biodegradable polymers. Yes? Scientists developed biodegradable polymers. That means, unlike conventional plastic, these materials can be broken down by microorganisms, yes, into harmless substance such as carbon dioxide, water, and biomass. Yes. Can anyone think why this is very much important for us? Yes, it reduces environmental pollution, supports sustainability, and also it develops it supports a sustainable development. Yes. So the best example or like biodegradable polymers, which we tell is PLA, polylactic acid, or PVA, chitosan, starch, cellulose, which all are naturally occurring polymers or like biodegradable polymers. So biodegradable polymers are nothing much or nothing other than polymers that undergo degradation by the biological process such as microbial enzymatic action, and which will lead to conversion of completely into a natural substance. Yes. So like carbon dioxide, like water, biomass, or any other inorganic compounds. So now let us understand how the biodegradable polymers can be classified. So broadly, when we talk, biodegradable polymers can be classified into three different categories. The first one is natural biodegradable polymer, second one is synthetic biodegradable polymer, and the third one is semi-synthetic. Yes. So natural, obviously from the name itself it is very clear, it occurs from the nature. It is for the biodegradable polymers which comes from the nature, like plants, animals or microorganisms, where we can include like starch is there, cellulose, chitosan, proteins, natural gums, all these things, because all these are produced by the living organisms directly, or like microorganisms, or we can easily recognize and degrade them also. Yes, or because of all these reasons they are considered as a natural polymer. The second category is synthetically produced. That means from the, or like as we told about synthetic polymers usually, right, manufactured through a chemical process, but it can be, or it is designed in such a way that it can be broken down by enzymatic action or environmental factors. Yes, so synthetic biodegradable, but can be action or can be still degraded by an enzymatic or like environmental factors, that are known as synthetic biodegradable polymers. For example, we told about PLA, right, which we told like as a best example. PLA is there, PGA, PLGA, all these are like, or like PVA or PCL, all this polybutylene or polycaprolactone, all these are like best examples for thermosynthetically biodegradable polymers. Yes, so natural polymers, as we told, it is like which is coming directly from the nature, and semi-synthetic, it's like which is synthesized by a human, but in such a way that it can be degraded naturally. Yes, that is synthetic. Now, third category is like when it is microbially derived biodegradable polymer. Yes, it is genetically modified organisms. In that case, what happens? These polymers, as we say, are synthesized by direct microorganisms as a part of their metabolic process. For example, polyhydroxyalkanoates, or like polyhydroxybutyrate, polyhydroxybutyrate cohydroxyvalerate. So all these are like, which is commonly abbreviated as PHA, right? All these are like synthesized from the microorganism as a metabolic process of them. So they are directly derived from the microorganism. So these are the three categories. First is natural biodegradable, second one is synthetic biodegradable, and the third one we say that naturally occurring but happens as a process of the metabolism. Yes, so these are the three different types of classification, major or broad classification for a biodegradable polymer. So when we come into, so I hope this classification is broadly understood. Yes, now let us look each like examples. Yes, some of the important biodegradable examples for biodegradable polymers, right? Let us see. Before going into the categories or like different examples of biodegradable polymers, let us think why this have like different properties or like common characteristics. Is this materials having common characteristics? Yes, the main characteristics is that they have the ability to degrade naturally without causing a long-term environmental pollution. That is the major or like highly common category for all the biodegradable polymers classification. Even though they are classified into three categories, the main characteristics is like naturally degradation. So that is why, or this is why biodegradable polymers are considered one of the most promising solution for addressing the global plastic waste problem. Yes, so by this usage of biodegradable polymers, environmental pollution can be reduced to a maximum. Now, as we understood what is biodegradable polymer and how they are classified, let us see on what does, or like let us see what are the important features and why this why the industries around us, yes, use them increasingly nowadays. Yes, the main feature for the biodegradable polymer, yes, when we talk, it is eco-friendliness. That is highly friendly, eco-friendly. They can be decomposed into non-toxic natural substance. That is the main advantage or like main feature. Second one, when we tell, so as always, we try to reduce the environmental pollution. So we need some material, some polymers which can be used so that it will be reducing the environmental pollution. So like that materials are biodegradable polymers. Yes. So second feature for them is renewable source. So when we say, they are like often this all the biodegradable polymers, they are often derived from a biomass such as corn, sugarcane, cellulose, starch, chitin. Yes, they are always derived. We get all this from our renewable sources itself, which is not even stopping. So when we, as we talked about like eco-friendly, no? So what will happen? They reduce, or they help in reduction of the soil pollution, water pollution, as well as other harmful microplastics also. So that is why everybody nowadays are changing their research work or their interest application into something based on the biodegradable polymers. The main feature is eco-friendliness of the material. Okay. So the next category or second important feature is that many biodegradable polymers comes or like are obtained from a renewable source. Yes, renewable source. Now, what is renewable source? Which is obtained from our being our surrounding itself. For example, like when we talk about PLA. Yes, PLA can be obtained from a corn, sugar, or like normal corn starch, or like sugar cane. While cellulose, it is obtained from the plants and agricultural waste. We sell that agro waste. Okay, so these materials, that renewable source, like as we tell, that their raw materials can be replenished or like changed naturally. Yes, unlike petroleum based plastic that depend on finite fossil fuels, we don't have to depend on any other thing. We have everything around us. Even the agro waste materials can be used as a source for the biodegradable polymer. Yes, so main advantage of using such material is like it reduces the carbon footprint. So the production and degradation of the material or of the biodegradable polymer will generally reduce the greenhouse gases when it is compared with the conventional plastic. So normal, like all the plastic which is normally made from the petroleum based material, so there will be a less amount of greenhouse gases emission. And the highly challenge or like highly attractive is that a feature of them is that it can fight against climate change. Yes, reduce footprint, carbon footprint is reduced. So climate change, it can be withstanding. So the next important property for them is like compostability. That means that many biodegradable polymer can be converted into a compost. Yes, under the controlled conditions. So we can control the conditions which is needed. Sometimes it can be 60 degrees, sometimes high pressure or like high temperature, or like a use of enzymes or anything. So all these like a controlled condition where it can be controlled, or like is when the biodegradable polymers can be converted or like degraded. Next property or like next feature where a biodegradable polymer is main property, we can say that it is biocompatibility. So now what is biocompatibility, or what do you mean by compatible? So nothing. Compatible is very simple, which can be used. Yes, when comes bio, then it can be used within the body. So since we are using the starting material or the raw material such as corn or sugar cane or cellulose, starch or chitin, what happens? These are non-toxic material. So they are like highly safe to be used within the body. It can be interact safely and living tissues. So what happens? They will be used. So wherever there is any biomedical uses, right? So there all things can be used. So for example, like when we talk PLA or like chitosan, they are highly used for tissue engineering or like wound dressing, drug delivery system or surgical implants, right? So you might be knowing about the bone implants, right? When a fracture happens or a bone is broken, what usually people do, they will be keeping a steel plate or a rod made up of like steel, obviously, or like a stainless steel or like chromium, cobalt alloy, all this. Now instead of that, if we modify some features for this biodegradable material, we can use this as a implant material. So it is like highly useful, so highly biocompatible. Yes. We also like can save, since it can be like used as a biomedical purpose. What is there? It can be highly stable inside the body. There is like safe degradation happening inside the body, so that it will be having low toxicity and safe degradation inside the body. So there is no byproduct or like harmful byproducts when used in the body. Yes, so when biodegradable polymers decompose, they generally produce substances that are harmless to humans, animals, and the environment also. So this significantly reduces what environmental risk when we compare with the conventional plastics, right? So last or like main property which we can say, or like feature which we can say, is like mechanical property. So what will happen with the mechanical property? Many modern biodegradable polymers, what will be there? So they will be having high mechanical property. So they can mimic usually traditional plastic in the strength and processability. That means instead of this, instead of using a Teflon or like any other material like which we use in the strength, right? So this material, biodegradable polymers, can be used because they can provide high strength, flexibility, transparency, and processability, like for example for packaging or industrial or like agriculture, biomedical, or any other consumer products that can be used. So from this like slide, what we understood what are the main feature for a biodegradable polymer. What are the main feature? Main feature is eco-friendly. That means it can decompose into nature with a non-toxic substance, right? Second is renewable source. Third one is like reduced carbon footprint. Fourth is compostability. Fifth one is biocompatibility. Sixth is like low toxicity and safe degradation. And seventh is like highly similarity in the mechanical properties. So all these reasons make the material or like biodegradable polymer as a best industrial material, or like in another word we can say that industries no longer need to sacrifice the performance in order to achieve the sustainability. Yes, these are the polymers, or like we can summarize like these polymers are like environmental friendly, renewable, compostable, biocompatible, safe, and mimic or like is helpful in delivering useful mechanical properties, right? So now let us see, or like with an example. Yes, let us see the example for polylactic acid. Now what is polylactic acid? So which is like, this is one of the most successful biodegradable polymer. Yes, why this is very successful? Because it is highly prepared or like made from lactic acid. As in the name polylactic acid, it is produced from lactic acid. From where this lactic acid is obtained now? It is obtained by the fermentation of starch or sugar. Where is this starch or sugar? From the natural source like corn, sugarcane, or cassava. Cassava's other word is tapioca, which is used in India. Like it's again a rooty vegetable. Yes, so these are the main raw material for polylactic acid. So when corn, sugarcane, or cassava is fermented, yes, the starch of it is fermented, we usually get a lactic acid, which is the starting material for polylactic acid. So lactic acid, when it undergoes dehydration, what will happen? They will form a lactic acid oligomers. Oligomers means small chained polymers. Yes, when we told in the like previous class, we told like when it is like molecular weight is high, we use it for a better industrial application, right? Because as the molecular weight increases for the polymers, what will happen? Strength of the polymer also increases. When it is long chain polymers like more than 75,000 and all, if the molecular weight is there, then we say that degree of polymerization, in another word, degree of polymerization, when the degree of polymerization is more than 75,000 and all, we say that as a long chain. Yes, when it is short, like around 50, below 50,000, then it is known as oligomers. Yes, even though it is a polymer, it will be known as oligomers. So oligomers. So lactic acid, when it is dehydrated, we will be getting a lactic acid oligomer. So lactic acid oligomer, when it is cracked thermally, that is broken into cracking means giving a break, right? Giving a crack. How we are giving the crack? By thermally, by giving heat. When it is heated or given a thermal cracking, we will be getting a lactide. So lactide, what happens? It is a closed structure. It is a ring closed. Yes. So when it is undergoing a ring opening polymerization, we will get our final product as PLA, or like polylactic acid. So lactic acid, which is obtained from the corn, sugarcane or cassava starch and fermented, the raw material lactic acid will be there. Lactic acid, as soon as it is undergoing dehydration, we'll be getting lactic acid oligomers. Lactic acid oligomer, as undergoes like thermal cracking, we'll be undergoing like we'll be getting lactate, and lactate as a closed structure. So when it is undergoing a ring opening polymerization, a PLA is obtained. So this is PLA. So this is the normal synthesis for polylactic acid. Now, what are the main properties, right, for the PLA? So as we say, biodegradable, obviously. PLA is the best material for biodegradability. So biodegradable. So how it is biodegradable? It can be combustible under controlled conditions. That means if a specific temperature is given, then the biodegradability or like the material gets degraded. Highly transparent. That means it gives a good clarity like PET. PET is nothing but polyethylene terephthalate, which is used in our normal bottles, PET bottles, right? So it can be, now PLA comes into action over there. Yes. High strength and stiffness, which can be compared polystyrene, which is a synthetic polymer, right? Polystyrene. It gives strength as polystyrene, very strong. Then thermoplastic, it is thermoplastic, yes. So how it is? It can be molded, extruded, 3D printed. We can do in any way and made it as a very good thermoplastic material. Then biocompatible, since it is biocompatible, since the starting material is corn, sugarcane or cassava, the starting material is raw material like normal natural material, so it can be used as a biocompatible material. So it can be used highly in the medical fields. And low thermal resistance, that means it can withstand the temperature into a lower temperature only, so which is a negative impact, that it is lower than the conventional plastic. So as long as the plastic is considered, normal plastics are considered, we cannot withstand up to that plastics, yes, that temperatures. So this is all about PLA. And since PLA is like highly used, where PLA is having good properties, it is highly used in food packaging, yes, and 3D printings like for biomedical implants, tissue engineering, textiles, all, or like agriculture, all these areas it is like used. So when I talk about like packaging material, you might have seen in the food containers, right? So the covering of the food containers, which is a transparent wrap, that is made up of PLA. So biodegradable or like biomedical devices, I told, like as I told, like it is like bone implants, right? Resorbable bone implants. That means the implants which instead of steel or like stainless steel or like this, we can make it into this. Then for textiles, cosmetic packaging, the bottles of cosmetics, all are like PLA material. So this is how PLA is into action. Yes, or PLA is used in an application level across the industries, right? Now, let us see another beautiful example. These are like beautiful examples for PLA, as I told, right? So for the glass, whatever we are drinking, no, that water glass and all disposable glass, it is made up of PLA. That sheet tray, this is like highly PLA material. And fabrics, all the fabric which is like it is having 100% PLA, like knitted fabric, it is like 100% PLA. This is also, here the PLA is 85% with 15% acetic acid. Here it is 34% PLA with 66% polyester. So all these are like plastic PLA application. And biomedical, as you can see from the picture, it is like highly into tissue engineering, training, like simulators, radiotherapy, surgical instruments, everything is there as a application for the PLA. Yes. Now let us see. Now let us see another example for biodegradable polymer. Yes. Have you ever eaten a shrimp or crab? Yes, no? Yes. So what we usually do, we threw away the shells of shrimps and crabs, right? When it is cooked or like boiled or like before that itself, we clean off the shells and we clean the only that fleshy part, right? So the shells that are often discarded as a waste material from the shrimp, crab or insects, right? So this material contains high amount of chitin which can be converted into chitosan. Yes, so how beautiful example is this, right? Converting a waste into a valuable biomedical material. So chitosan usually is having a high or like excellent wound healing property, which can be used in drug delivery, water purification and food packaging applications, right? So can you see all this? Mollusks, cramp, sorry, mollusks, crab, shrimp, yes, algae, fungus, insects, all these are like high sources of chitosan. So when that like high sources of chitin actually. So when this chitin is polymerized, we will get chitosan. Yes. So this is the structure for a chitosan and these are the raw materials for chitosan. So chitosan will be obtained as a chitin from this shells of these insects or like crab or shrimps. Then it has to be undergoing polymerization, will be converting into chitosan. Yes. So when this is done, it is like highly water soluble. What are like highly water soluble but forms good films. So as we can say, since it can be formed as a films and water soluble like insoluble, what is the property? It can be used as an excellent wound healing property. It can use for example like as used as a bandage material for the wound healing. Non-toxic obviously, since all the raw materials are like naturally occurring, non-toxic. Yes. So wound dressing, drug delivery, and it absorbs heavy metals. We can say we can use it in the food packaging films also. The as I told for the PLA, the covering materials, right? Transparent cover that can be used in the food packaging films. And for agriculture, we can say like if we add this shells or like chitosan material, what will happen? The growth of the plant will be enhanced. Improved growth, crop growth will be there. Yes. So this is all about chitosan or like chitin. Yes. Another example we can talk is like starch or like cellulose and all. So cellulose, as we see, it is like the most abundant natural polymer on earth crust. Yes, highly available. So where it is, every tree, every plant stem and like every other cell walls or every other leaf contains cellulose. So like researchers are now converting agro waste materials such as rice husk, maize husk into nanocellulose. So why is like nanocellulose exciting for us? What is the main feature? So what is it? This is because like nanocellulose material is stronger than many other conventional materials. So it is highly lightweight. We knew that, right? Rice husk and all, if you have touched, it is like highly lightweight but highly biodegradable. So because of all these things, nanocellulose material is like highly used or like and abundantly found on the earth crust. So it can be diverse natural sources. We can get it from wood and cotton fibers. We can get it from natural residues like rice straw and maize husk, bacterial cellulose, marine algae, all this. And it can be modified as an application what we need. Cellulose ether, we say HPMC, like hydroxypropyl methyl cellulose. It's like here the viscosity can be controlled, drug delivery can be controlled. Yes. Next is cellulose ester. All these are like modification of cellulose only. Cellulose acetate. Yes. If you remember the candies, wrappers and all. So all these are like cellulose acetate. Yes. Coating materials or like sustainable packaging material, or like we can use it in a 3D printing filaments also. So because of this tailored properties, what happens? It can be having precisely controlled solubility, mechanical strength can be improved, and biodegradation for the specific application can be tailored. So by all these properties or like all these features, or like when it is modified, cellulose can be the abundant or like natural polymer found on the earth which can be used in variety of applications. Yes. So what makes it like a unique property, right? Or like what makes it better candidate? So it is having a semi-crystalline architecture. That means the strong intra and intermolecular hydrogen bonds between the molecule. It's like it gives a rigid, stable structure with unique mechanical and characteristics. Yes, highly water insoluble. So even though they are naturally insoluble, what will happen if it is chemically modified? They can be like made as like ethers or esters and soluble. Then it is superior performance. It gives high tensile strength, biodegradability, and stability, like chemical stability and complete non-toxicity. So, and it can be formed in different polymorphic forms. So usually first, second, third and fourth forms of nanocellulose material can be found, and which will influence mechanical behavior and chemical reactivity. So by all these features, cellulose make itself as a unique material or like a strong biodegradable material. So I hope with this and you might know I hope by this we can understand the importance of cellulose, where all which all industries it can be used. It can be used for the food packaging, it can be used in the agriculture, it can be used as a biopolymer reinforcement, it can be used in pharmaceutical, it can be used in bacterial also. Yes, so medical innovations by using of bacterial cellulose. So n number of applications are there for cellulose, and all this makes it as a best biodegradable material. Yes. So before we end today's lecture, let me ask you a final question. Yes, if you are an engineer asked to design an environmentally friendly packaging material, would you choose a conventional plastic or a biodegradable polymer? Which one will be your answer? So as a chemist, my answer would be a biodegradable polymer, because like today's world needs material that balance performance with sustainability. So as a conclusion, in today's lecture we understood what polymers are, yes, and what biodegradable polymers are, especially how they are classified, what are the different biodegradation time, and few examples like PLA, chitos and cellulose, and why they are considered as the future of sustainable materials, right? So thank you, students. In the next lecture, we will continue our discussion with plastics and their engineering applications. Thank you.